I'd like to welcome you all to our session, or panel session this morning. As you can see right here, Electronics Innovations Great Leap Forward, not with any purple journalism or anything. An overview of the JUMP program. My name is Linton Salmon. I'm a program manager at the Defense Advanced Research Projects Agency, DARPA, and we're a participant in the JUMP program, as I'll discuss in just a minute. And I'm joined by four academics, university professors who are members of the different centers in the JUMP program. So the purpose for the JUMP program from a DARPA perspective is that it drives pathfinding research efforts, and by pathfinding I mean at least 5 and more likely 10 years out. These are advances that would start to be used by industry in 10 years, or in the case of DARPA, that we would start using in DoD systems, in new computing and communication technologies through a collaboration. And the collaboration exists, as you can see over here. There's DARPA, representing the United States government, academia, that are the performers, and you'll see the 4 representatives up here in front of me, as well as industry. It turns out that funding, the majority of the funding for the JUMP centers comes from industry, from a number of different companies, 13 different companies, and then DARPA provides a large amount of money as well. So it's to drive long-term research in microelectronics with key players in the industry and from academia. And the purpose is to develop long-term research themes that have to be done at scale. In other words, each of these centers is on the order over $5 million per year of funding. Collectively, they have over 120 faculty members and over 600 students. This is a lot of intellectual horsepower, and the purpose for the JUMP program is to harness that power so they can be used to address the critical technical challenges that will be facing the industry in the 5 to 10 year time frame. There are 6 multi-university, multidisciplinary research centers. It's focused on 6 long-range microelectronic research themes. There's DARPA plus 12, excuse me, I got it wrong, there's 13 total, 12 industrial members as well as DARPA, and roughly $40 million per year that's anticipated for 5 years funding, collectively between DARPA and the industrial participants. And as you can see here, 132 faculty and over 700 students. These are the individuals that you'll be hearing from today. You'll hear from Professor Arijit Chowdhury from Georgia Tech. He will be talking about the Ascent Technology Center. That is a center that focuses on materials, devices, and packaging for microelectronics. Professor Kaushik Roy, who was the director for the CBRIC Center that is focusing on cognitive and machine learning activities out in the future. Professor Yuan Shi, who will be discussing, who is representing the CRISP program, which is a CRISP Center, which is talking about intelligent memory. As you all know, memory is a critical portion of almost all of our discussions, and the CRISP Center is focused on that. And our final and best speaker will be Professor, yes, you're welcome, Professor Valeria Bertacco from University of Michigan, and she's the director for the Ada Center that focuses on algorithms and architectures, on design, if you will. So without further ado, I will turn time over to Professor Arijit. If you could move to the next presentation.
All right. Thank you, Linton. All right, I think this is working. So I am going to give you a brief overview of the Ascent Center, which is the Center on Materials and Devices. The director of the center is Suman. He couldn't be here today. I am one of the team leaders in the center. This, at the moment, I think is the largest JUMP center with 30 PIs and more than 130 students. So the whole center is kind of subdivided into 4 themes. So the research is being conducted in the first theme is essentially on vertical CMOS. The major problem there that we are trying to address is monolithically grown back-end-of-line transistors and memory structures. So that's essentially the crux of the vertical CMOS theme. Theme 2 is beyond CMOS, which is essentially looking at state variables which are not charge-based. The major focus there is looking at spintronics, starting from both memory systems as well as logic operators. And there is a significant amount of work and resources being dedicated to this beyond CMOS theme. The third theme in the research vectors is essentially heterogeneous integration. This is more about advanced packaging, where you have heterogeneous dies, maybe sourced from different technologies, put together in a system, in a package kind of a configuration with high bandwidth I/O and high density. So I'll talk a little bit about some of the challenges that we are trying to address in that theme. And the last one is kind of an interaction between is an interaction between logic and memory. So this is where we are looking at applications and software and how that maps into advanced circuits and systems. So this is a brief overview. I'm not going to go into the details of who all the performers are. So these are all the PIs who are involved in the in this particular center, Ascent Center in the JUMP program. So going to the first theme, so this is the vertical CMOS, as I mentioned. The basic idea of vertical CMOS here is to be able to get very high density transistors in a 3D configuration. And for this particular theme, we're looking at monolithic integration. So if you think about, in terms of material discovery, there's a lot of work that needs to be done to be able to get good transistors at back-end-of-line temperatures. The major challenge there being when you grow transistors in the back-end process, it has to be grown at a lower temperature, which means the transistor quality is not going to be very good. So, so there is a lot of work going on understanding what kind of materials. These are definitely not silicon transistors. There is some work on silicon transistors, but there is also a lot of work on oxides and other kinds of transistors, which can grow in the BEOL process at low temperature. One of the major applications for that would be access transistors for a truly 3D kind of a memory configuration. If you have dense memory in the back end of line, then how do you provide access to those devices? So we are looking at both 2-terminal access devices as well as 3-terminal devices. A good amount of work is going on ALD, particularly hyper-selective ALD. We have to provide a very high conductivity in these back end of line processes, which comes with its own challenges. Apart from all of this, of course, we always want to work on front end of line transistors as well. So there is a good amount of work going on essentially scaled transistors. How do you improve mobility and electrostatics and all that? So these are some of the major highlights in this program has been going on for almost 1.5 years now. So these are some of the major highlights from that from that work. So there has been some interesting work on ALD, particularly on both computational ALD as well as looking at material choice for ALD with applications to contacts and vias. Andrew Kumel has been a pioneer in that, and he has been doing some very interesting work with precursors so that you can have almost scattering-free conductivity. There is a good amount of work going on, particularly 2D materials and 2D transistors. With some of the measured results show some of the lowest off currents to date, and these have excellent characteristics. For example, as access transistor for DRAM. So you're looking at attoamps per micrometer kind of currents. A good amount of work here for starting to build 3D transistors is thermal management. So a good amount of work is going on materials for thermal management, as well as I mentioned, 3D memory and selectors. So so this is kind of the overview of the vertical CMOS theme, where we are trying to grow in the Z direction, the height direction. Beyond CMOS. As I mentioned, the major challenge here is to be able to enable spintronics. STD-MRAM, the spin transfer torque memory, has been around for a while now. In terms of it's kind of becoming commercialized. The major problem there is, of course, the write currents. They have very high write current density. So one of the big research themes here is to be able to reduce the write current as well as increase write speed for STD-MRAM, and that can be done with some voltage-dependent anisotropy structures. So these are some of the major work that's going on in that beyond CMOS theme. Again, without going into the details, the major application there is embedded memory. The third theme is heterogeneous CMOS. As I mentioned, this is like a system on a package. So here the idea is to get BOL kind of densities, but on a package. So we are looking at both glass substrates for high frequency as well as silicon substrates for more of digital applications. One of the enabling technologies has to be high-speed connections between these chips or chiplets. A lot of this work came from previous DARPA programs, but we are extending beyond that, looking at things like pseudo-lithic integration, where you take one die and then place another die on top with BOL kind of densities, and whether you can grow BOL processes after that and get very high logic and memory density. This is kind of the big vision. How do I enable like the Moore's law of scaling for packages? I think that's the big vision of this theme. I'm not going to go into some of this. So we have a lot of work going on radio architectures as well. Comm center is the communication center. There is collaboration going on how do you build antennas, how do you build waveguides and silicon integrated waveguides, particularly SIF structures on the substrate, so that you can hit very high, very close to 60 gigahertz, 100 gigahertz kind of frequencies. And the last theme is essentially merged logic and fabric, where we are looking at putting things together, the logic and the memory fabrics together, and to bring high energy efficiency for workloads like machine learning, graph processing, encryption, and so on. So a lot of the work in this theme is essentially to interface with the vertical centers that Kaushik and Valeria and Yanji is going to talk about. So I'm going to stop here, and otherwise Linton is going to beat me up. So.
One of the big challenges for this is to get academics to talk in 6-minute increments. It's extremely difficult. Each one will spend 6 minutes talking, and we'll have 15 minutes or so at the end for questions.
Kaushik? Thanks, Linton. What I'm going to talk about is some of the work that we've been doing at the Center for Brain-Inspired Computing. I'm Kaushik Roy. I'm the director of the center. And there are actually 19 faculty involved from 9 universities. Now, certainly deep learning has made a huge amount of progress in the recent past, right? And in fact, today you see that at DAC, there are so many sessions on deep learning. However, in fact, we use deep learning in almost everyday use today, but there aren't really that many, killer applications. And the killer applications might include self-driving cars. It's not there yet. It's going to take a while. A swarm of robots flying together with collective intelligence, and so on. Now, in order to really get there, there's a need for really thinking, going much beyond what deep learning can do today. Today's deep learning is mostly perception-centric. However, there's a need for really thinking about not only perception, reasoning, decision-making, and so on. But at the end of it, there's also a thing about robustness that I'll talk about. But in order to really do that, the vision of our center is to really enable the next generation of intelligent autonomous systems by harnessing the key information processing principles of the brain. And I'll go into that in just a minute. But before that, let's try to look at what's today's deep learning systems are. Today's deep learning systems, when you look at sort of like, training an algorithm, they're usually, stochastic gradient descent based, and the validation of some of these, algorithms are really mostly empirical. They're usually implemented in a von Neumann kind of machine, which are really, as we all know, the GPUs and, the TPUs and FPGAs. And finally, at the end of it, if you really think about learning, that mostly resides in the cloud. And there are actually systems coming up where the intelligence also resides in the edge devices. But what we feel is that there's a need for really thinking about distributing the intelligence between the edge hub and the cloud. And that can potentially lead to energy efficiency. And finally, also, there's a need for really thinking about distributing intelligence when you're thinking about flying a swarm of drones together. And if they were to see different kinds of environment, they would actually have to communicate with each other, and at the end of it, come up with some collective intelligence to make a decision. So the need for distributed intelligence is absolutely there. So with that in mind, if I were to really look at what CBRIC is going to do, is we are developing new algorithms, which are neuro-inspired algorithms, bioplausible network architectures and algorithms. Now, the reason why I bring about bioplausibility is because we know certainly that brain is very efficient, and bioplausibility, we feel that is a really means to an end to, to achieve energy efficiency. Now, and these algorithms can lead to perception, reasoning, and decision making. And again, going much beyond what today's deep learning can do. Now, another area that turns out to be quite important, today's deep learning, we don't even know why some of these things work and why they don't work in some cases. So it's like a black box. And in order for really deep learning to be widely applicable, there's a need to really think about having more theoretical understanding and analysis of things. So to that effect, as a part of our center, we have a good amount of work which is going to be going on theory and robustness of these deep learning systems. Can I really come up with systems which are robust? Also, there's a huge amount of work which is going on today, for example, in the area of new devices. The new devices or neuromimetic devices that can sort of mimic the neuron and the synaptic functionalities in some efficient way. And Ascent, as Orijit was mentioning, is working on some of those. So we are jointly working with Ascent to develop these new algorithms which are suitable for some of these emerging hardware fabrics. Now, since I talked about these algorithms, they need to be implemented certainly in an efficient hardware. For whatever little that we know of the brain's architecture is unlike a von Neumann machine, where I don't have a CPU on one side and memory on the other side. It's all distributed in nature. And to that effect, taking cues from the brain, the question, of course, is, hey, is it possible that I come up with in-memory computing primitives, which could be in CMOS or could be in other non-volatile technologies, and that can potentially do certain kinds of computations which are very suitable for some of these deep learning applications. Can I do effective or energy efficient inference and training on some of these architectures? Inference is certainly important, but training certainly takes a long time. Can I do that? And finally, at the end of it, approximate, stochastic, and Shannon-inspired hardware turns out to be quite important. And as I mentioned, distributed intelligence, I'm not going to go into the details of it, that plays a role. In order to do that, in order to evaluate where we are, turns out there's a need for really thinking about some matrix, and our matrix is going to be energy delay improvements in training and inference. And this is basically showing where we are today, and the need for us to be is a target area that I'm showing, which would require us to really think about algorithms, hardware, to be able to give us about 200 to 300x improvement over what we can achieve today. And that we are working with actually application drivers like drones, which are going to give us basically the data sets and all these different constraints. But I'm going to end with the fact that it's been a year, and I'm going to show some of the artifacts of year one with some prototype chips that we have already developed. I'm not going to go into the details of any one of these, but these are all, for example, this is on the right where I'm showing a reinforcement learning chip for edge robotics. These are actually XNOR RM monolithically integrated in a 19 nanometer CMOS technology for in-memory computing, and so on. And this is also, some of the other software-level artifacts showing actually drones flying with some of the algorithms that we developed on reinforcement learning, some of the implementations in the Loihi hardware, and so on. So I'm going to end with that. I hope I haven't taken too long.
Hello? Yeah, what I'm going to talk about is actually following Kaushik's statement saying that the human brain is actually, there's no distinction between compute and memory, right? So our center, CRISP, is representing for our Center for Research on the Intelligence, Storage, and Processing in Memory. So basically the motivation is actually looking at the logic and memory latency and energy gap is that the computing, the performance increased more than 50% per year. But on the other hand, the memory performance increased by only 10% per year. And furthermore, the data movement for today's computer architecture where you have a compute and memory separated, the data movement between the memory and the compute is actually very expensive. When you look at the energy to do the computing versus the energy to do the data movement, you can see that the order, it's about orders of magnitudes, okay? And this type of a gap doesn't disappear as the technology scaling. In fact, the percentage of the data movements overhead remains to be a large portion of the total energy. Okay, so for that, because of that, we need new architectures to leverage the emerging technology that can achieve the integration and also bridge the gap between the compute and memory itself. That's the reason that why we are looking at the intelligent memory and storage. Okay, so the grand challenge for us for this center is try to remove the memory and the I/O bottleneck to operate at the data flow speed of the light, and making the programmer's life easier, making programs intend to hardware do it so efficiently. And we also take the approach of application-driven innovation, look at what applications would be the killer applications that can enable this type of intelligent memory and storage. Okay. And this is the big picture of the center. Basically, you can see that we have three major themes. Okay, at the bottom, we look at different type of memory technology, including today's SRAM, DRAM, hard drive, and solid-state disk, as well as the emerging memory technology such as this non-volatile memory, such as STT-RAM, phase change memory, resistant RAM, and so on. Okay, and we look at it from the circuit architecture perspective in the theme 1, look at hardware support for massive parallel hierarchy processing in memory and storage. And then in the theme 2, we look at system support for this type of enabling this kind of intelligent memory and storage. At the higher level, the theme 3 is actually looking at the application and also programmer's perspective. Okay, what are the killer applications that can benefit from this type of intelligent storage and processing in memory? Okay. Now, the research plan we are looking at is actually in the last 1 year, we actually looking at novel architectures and also looking at compiler support programming models, as well as the killer applications such as new benchmark that can drive our research. Okay, our grand challenge is to lower the effort for everyday programmer to achieve highly portable and understanding the performance across a wide range of heterogeneous intelligent memory storage architecture. Okay, thank you very much.
Good morning, everybody. Before being an academic, I worked for several years in the EDA industry. And in that role, my job was, like many of your job, to create tools that let people develop better hardware and better software that creates new devices that change and improve people's life. Right? System innovation has been going on since the 70s in a pretty steady state, and that's what has created this industry and changed the way we do computing or pretty much everything else. Unfortunately, there are a few problems that are emerging, and these innovations started to run on empty fuel tanks. The first one, as you all know, silicon innovation has slowed down. Scaling has slowed down. We have problems of dark silicon. There are a number of problems at the silicon level. You also, I'm sure, are extremely aware of how unmanageable it is to design the system of the complexity level that we have today. One problem you probably don't think very much about is how we have application today that could change people's life if only we had the hardware to run them. There is a gap, a growing gap between the demands of software application and the computing power that we can provide. And so these three problems are what the ADA Center is trying to solve. We formed the ADA Center specifically to reignite computing system innovation by addressing the problem that is slowing that down. So the type of problem we want to address is how do we find new ways to create value in computing system? If silicon cannot make the cut or continuing to provide innovation, can we leverage architecture to do that? Computing system architecture, and how do we do that? People are probably not coming up with smaller transistors, but they're coming up with different things you can do with silicon. Can we leverage that to get benefit at the computing system level? Manufacturing is skyrocketing in cost. Can we find different ways to do manufacturing that is composable and scalable so we can lower cost? And then the other big dimension of research is design flow is extremely complex. You cannot do hardware design with a bachelor degree, right? You need to have advanced degree and be able to manage in a team a very high level of complexity. So can we have much faster way to turn around? When a new application comes, can we have faster way to develop silicon for it so that we can accelerate it? Think about machine learning. People have been talking about machine learning changing the world since 2009, 2010. Now we start to have silicon for that. It took a decade from software to silicon. And then the other aspect I really would like to address is, in order to reignite innovation, we need to have many, many more people who can develop computing system. We cannot just have a handful of hardware designers here and there. So we need to democratize the process, and to do that, we need to make the process much more accessible. It should require much less specialization in education. So this is my new rocket, the ADA rocket, that can innovate in computing systems. Our center is organized along 3 themes. There are people that work on developing new architecture to create innovation, people who develop agile system development, basically new design flows with specialized design languages, and then people who explore emerging technology, this doesn't click, and figure out how they can be embraced in the design flow system and what benefit do they bring at the application level. So the end goal of the center is to enable an ecosystem that allow quick enable of new applications that are emerging, and in a way that is easy for developers, and I'm being vague on purpose here of what is a developer, to design and utilize new silicon. And I'm being vague because I don't want these people to be highly specialized. They should be able to do it without high specialization. So, this is an old version, I'm sorry. These are a couple of projects that Linton will kill me if I talk about, so I won't. One of the things we want to push is a design flow framework where researchers can deploy their new idea and evaluate the impact they have at the system level. We don't expect to be the sole group of people that can come up with new solutions. So we want to have a framework where you can plug in your new solution. On the left here, we have domain-specific languages. There is a blooming of domain-specific languages. They are fantastic because they let you describe complex application with very little code, right? They have very powerful primitives. But we need to have some infrastructure to manage them because they are growing like weeds everywhere. We need to have structures to compile those domain-specific languages into hardware through intermediate representation. And that's another very rich domain, from front-facing to back-facing intermediate representation. And then we need to have an infrastructure when people can plug in architecture solution and device solution to evaluate new final devices. So the team has 20 PIs, 90 PhD students. We are distributed among 8 different universities. We started the Lynn Conway Research Award for our students. We held 3 symposium days. In the last one that was held in April, our students presented demos. We had 23 different demos. And these are all our sponsors that really closely collaborate with us. They dial in into meetings where we discuss research. They tell us about their problems. So we try to be closely connected to the need of the industry in directing the research. Thank you.
So I don't know if they can figure out who's supposed to be on the microphone next, but so I think you can agree they met it in the time frame. I'm impressed. We should all give them a big applause for doing that alone. It's amazing to get all of 5 speakers in 30 minutes. At any rate, the reason we wanted to push it to 30 minutes was because we wanted to give you an opportunity to ask questions of this august panel. So if you have a question, if you want to walk forward to one of the microphones, please feel free to do so. And I will, go ahead.
Hi, this is Jolie from Cadence. First, thank you for all the panelists. It's a great summary, and it's one question is, so those 4, I can see, each of you has run a big center, lots of things going on. Of course, it's a whole ecosystem, I just have a question, like how often 4 of you or your program also talk to each other? And do you have some idea or some plan to integrate all of things together, like maybe with some of the new CMOS technology, put it on the best algorithm with the rocket system and with the latest memory, So do you also, so just want to get a sense how often, four programs also talk to each other and how you work together.
Can I speak?
Yeah, go.
Am I amplified? Yeah, okay. So, well, Kaushik and I were taking pictures together last night. So we meet together, I would say about 3 times a year in person among all the directors, usually probed by some of the sponsors. And the directors kind of have an overview of all the projects going on in each of the centers. So through those discussions, we can figure out what are the most appropriate connection points among different PIs. The centers have been alive for 1.5 years now, and I think we have over 10 collaborative research projects going on right now, but it's just growing.
Yeah.
Just to add, we actually had, even at DAC, a couple of workshops, which were joint workshops, Seabreak, Ascent, we had a workshop together. ADA folks came and presented, so did CRESP. So, and ADA had a workshop here too.
Yes.
So, yeah.
So we had a workshop on near in-memory computing on Sunday.
Yeah, and I think the best collaborations or best conversations are always going on amongst the students, and I think that's that really helps the process.
Yeah, I think that we also have multiple PIs actually sitting in across centers. For example, in the in-memory computing center, we have VJ actually is also in the Seabreak center and so on, right? So these also help a lot of the collaborations among the centers.
Given that we are a DAC about design automation, clearly EDA has some role to play in all your centers. At this point, none of the EDA companies are involved as sponsors. On the other hand, DARPA's, as part of ERI, is making significant investments in EDA. So I guess this is a question to Linton from the sponsor's perspective and maybe the directors as to, do you see a role and what role EDA might play in the research, but also possibly involving some of our companies in this or future center programs?
So my answer in general about who participates is they have to make a corporate decision. We've certainly addressed all of the EDA companies. Of course, we'd like to do even more research with even more researchers, but that requires more money. But they have to make individual corporate decisions about whether they'll participate or not. To your second question, which was about the importance of EDA tools and so forth, my general feeling is that most of these new innovations that we have, unless there is some kind of a software tool that enables designers to use it, it won't be very useful. So if you look at DARPA programs, but I would also say across these centers, one of the things that they're trying to do is to make sure that there are software design tools that will enable designers to use these new ideas to create better systems. And of course, the ADA Center is specifically doing that, but all of the centers have a component.
So one thing I might mention, this is something that was new to me. I even didn't know about it. But not traditional EDA, but a lot of software and computational methods are used in materials discovery. So many of the work, we apparently materials and physicists, you wouldn't associate them with DAC, right? But they are using machine learning techniques. They are using advanced computational techniques to build and synthesize metamaterials first, and then eventually work on experimental work. So there is EDA tools and computational methods which are kind of pervasive, even in materials and devices.
Hi, thanks for this wonderful panel and for putting it together. My name is Sharon Hu. I'm with University of Notre Dame. So I'm going to ask one question related to benchmarking, which is kind of pretty much close and dear to my heart. If I look at you all presented, actually, if I look at all your presentations, there are quite some similarities, right? You're all looking at AI type of related applications. You all do some sort of vertical chips to systems designs. And you all have your own some sort of comparison benchmarking. So I'm just wondering, from DARPA and from cross-center's point of view, how do you see, or what is the effort to really compare all of the different efforts in a fair, neutral way, instead of each center come up with a way?
So I will start. It's a great question, and then I'll leave it to my colleagues. And I think I represent not just DARPA, but also all of the industrial sponsors for JUMP, that benchmarking is a critical aspect of evaluation of the center and its value. It's important that we have some way of doing that. There's the danger. They're looking out 20 years, 10, 20 years from now, and if we make the metrics look like, well, it has to describe a von Neumann machine that we can implement today, so the metrics are a challenge, but I think each one of the centers has a set of metrics that they're using, and actually we've talked with the centers and they both coordinate as well as share many of those benchmarks.
I absolutely agree. Benchmarking, while it's very, very important, and we need to compare our results with whatever the standards are, we also need to be, these are new areas. We are doing new research, and hopefully that's going to be usable 10 years down the road. We need to be also careful about certain things in benchmarking. We don't want to stop a certain kind of research, which can potentially lead to, later on giving you better functionality, better learning algorithms and all. So interestingly enough, while benchmarking is absolutely important, as an example, some of the things that Ascent might be developing would be devices that can, enable new functionalities and can potentially lead to new learning, as an example. So those are the things that we also need to keep in mind when we develop our benchmarking. But every center certainly has an effort towards benchmarking.
Yeah, I completely agree. I think one of the main things is to kind of understand that figures of merit are very organic. So as the centers evolve and our own understanding evolves, the figures of merit keep on changing. We cannot benchmark, for devices, often it's easier, you know what the ION and the IOF specifications are, and you're trying to meet those. But as you abstract them to higher levels of abstraction, the figures of merit keep on changing. So I think that's something to be kind of cognizant of, and we have, as Kaushik mentioned, people working on specifically on benchmarking, and they are constantly trying to interface with other centers to understand how to abstract from lower layers of abstraction to metrics at a higher layer, which keep on changing all the time, right?
So you may know that each JUMP center is supposed to have a critical output, right? We're supposed to produce ideas, but they also want something tangible at the end of 2022. And 2 of our centers, as their tangible output, are supposed to produce benchmarks. So that's ADA and Ascent. From ADA is a more system level, right? Ascent operates more at the device level. So ADA to date has produced 7 different benchmark suites. Some are released through the APIs. Some are released directly from the center website, and they're publicly available. So an example of that is MilSpec, which is an end-to-end application that are defense-inspired. But we also have benchmark suites based on graph-based application, machine learning, and virtual and augmented reality. Some of this benchmark comes from tests that the other center use for their solution. So it's a way of collecting benchmark, distributing benchmark, and creating benchmarks.
I also want to add one more thing. For example, if you look at the processing in memory, intelligent memory idea, it was not new. Back to 20, 30 years ago, we already saw research on that, but it didn't take off. One of the reasons was that we couldn't find a killer application at that time. So that also gave us a motivation that while we are doing that intelligent memory storage research today, we need to identify this killer application that can benefit from this kind of merging the computing and memory together. So benchmark and finding the killer application indeed is very important for our center.
Yeah, I think one thing maybe also interesting to clarify is there's benchmark like data sets or applications, and there's also methodologies. And then also, what are the raw things you want to benchmark on? So I think 3 different things. And I think Kaushik brought up a very important point that maybe also to the sponsors in the sense of benchmarking is not necessarily, well, of course it's a purpose to measure the progress of the centers, but I think it's even more important is to tell the researchers where are the bottlenecks. And that's very important that we don't necessarily use it to say, we should kill this thing, or we should kill that thing. I think that, yeah, of course, that's part of consideration. But it's really, really important for all the researchers to learn. And that's why it's great to see even not quote-unquote successful things to be published, to let people know where the difficulties are.
I'd just like to finish up. We've got another 4 minutes, and I'd like to give a minute to each of you. If you were to project out to DAC 20 years from now, in your field, what would be the major issue that would be addressed here at DAC in 2040? One, you start.
It's going to be solved in 2040?
Nope, it's what, if you were looking here, I mean, today we talked about it being machine learning and those kinds of things. So what would that be in 20 years from now that has to do with your particular center?
You mean from 20 years from now?
20 years from now.
What would be the major research?
What will your field look like?
What my field looks like in terms of memory? I think that at that time, memory and computing, there's no distinction anymore. And that's the goal of our research center. I think that our center would actually help to achieve that goal.
Awesome. Valeria?
EDA would be much more accessible. And there wouldn't necessarily be a software to hardware boundary and separation. Like from the developer, it's just the system.
This is an interesting one from machine learning point of view. Yeah, I guess I'll have my, self-driving car waiting outside, take me home, and the robot will determine what kind of coffee I would want at that time, looking at my face and mood.
So does the robot also close timing and tape out the chip?
Good question.
Without pizza?
So I think from a devices perspective, materials, I think I can't, maybe, apart from all the radioactive elements, all other elements would be a part of a die. Because you're looking at all kinds of precursors now. So I think material discovery, and particularly from a DAC context, understanding computational methodologies for material discovery will play a big role, I think. And you will end up with metamaterials and kinds of materials that you cannot even think of today. And the result will essentially be, all these guys are saying, ubiquitous intelligence, data-centric computation, low power, all of this will be enabled by that. So I think we are just looking at this huge space of metamaterials that we don't even know of. So it will not be silicon anymore. It's not just, silicon will be of course, the backbone, the part of the process, but there will be so many other kinds of materials in the die. I don't think you can even project at this point.
Great. So I'd like to thank all the panel for